Welcome to Math 1508 Pre-Calculus at the University of Texas, El Paso. This lecture follows Larson's 10th edition of Pre-Calculus, Chapter 1, Functions and Their Graphs, Section 1.4, Functions, and this is going to be part 1 of 2 lectures for this section. I'm going to focus on functions here. So first, what is a function? A function f from a set A to a set B is a relation that assigns to each element x in the set A exactly one element y in the set B. The set A is the domain, or the set of inputs of the function f, and the set B contains the range, or set of outputs. Now this is important. Think of the input x as people. You can only be in one location at a time. It happens to be the spring semester. Super Bowl's coming up. I can only be at one Super Bowl party at a time. I can't be at my house and at my friend's house at the same time. However, a whole bunch of us could all go to my friend's house, or a whole bunch of us could go to my house. I'd probably be at my house if my friends came over, though. But one person cannot be in 2 locations. Bunch of people can all go to the same location. Let's think of that as we think of functions. What are some characteristics of a function? First of all, each element in A must be matched with an element in B. So everybody has to be somewhere. Some elements in B may not be matched with any element in A. Think of this as students in a university. Not every classroom is being used all the time. There are some empty rooms on campus. But everybody is somewhere. Everybody is somewhere, even though maybe not every classroom is being used at the time. 2 or more elements in A may be matched with the same element in B. So 2 people can be in the same classroom. It's all good. An element in A cannot be matched with 2 different elements in B. If you have a pre-calculus class scheduled at 10, you cannot also schedule a physics class the same day and same time. You'll fail one of them, that's for sure. There are 4 ways to represent a function. Verbally, by a sentence that describes how the input variable is related to the output variable. Numerically, by a table or list of ordered pairs that matches input values with output values. Graphically, by points on a graph in a coordinate plane in which the input values are represented by the horizontal axis and the output variables are represented by the vertical axis. And everybody's favorite, algebraically, using the equation in 2 variables, throwing our alphabet in with our math. Alright, so I'm not big on word associations because they can be misleading sometimes, but in general, they're kind of helpful. So we refer to the domain values as the independent variable because you get to choose it. And the range values depend on the domain value you used. Which classroom? Well, it depends on which student we're talking about. So independent and dependent. As the input value is x and the output value is y, we say that y depends on x, or y is a function of x. Now this is far too long for mathematicians to write out over and over again, so of course we have a notation for it. Y is equal a function of f, function f, we're not that clever, of x. And while f parentheses x looks like it's a multiplication, remember this is not multiplication. I'm not multiplying f times x. It's a function f, and I'm evaluating at x. Alright, so here's 3 graphs, and we want to determine if they're a function or not. Our test is going to be, does each x only go to one y? Well, it looks like here, any x I choose, there's only one y value that goes with it, so yes, this is a function. What about the one in green? Here's an x value, x equals 0, that has 1, 2, 3 different outputs. This is not a function. And if we look at the 3rd graph in gray, here's an x value that has only 1 output. Another x value that has 1 output. An x value that has 0 outputs, but it's not in the domain. But look, here's an x value, 0, that has 2 outputs. Here's an x value that has 2 outputs. It only takes 1 time for it to fail. But in this case, a circle, there are many different ways to show that this is not the graph of a function. Ordered pairs. If I have the set A, which is the set of ordered pairs 2, 3, 4, 5, and negative 1, 3, this is a function because two different x values, 2 and negative 1, can go to the same place, 3, right? You and your friend could have the same class. You could be going to the same Super Bowl party. But ordered pair set B, 1, negative 3, 2, 5, and 1, 7, is not a function because a single x value cannot go two different places. One cannot go to negative 3 while it's also going to 7. So that's not okay. But in set A, this is acceptable for functions. Alright, so equations. How do we test with equations? Pick any single value for x. I'm going to use x equals 0. Why not? It's easy. There are two possible y values. If x is 0, y squared equals 4, and then y equals plus or minus 2. Two values for y, not a function. In example B, y minus 4x squared equals 36. Take any given x value. When you substitute and solve for y, there's only one value possible, so this one is a function. Example C, x plus y squared equals 16. Once again, we only need one value that disproves that it's a function for it to fail. So any x value gives two y results. I'm going to use x equals 0. If x equals 0, then y squared equals 16, and y equals plus or minus 4. It's not a function. In example D, since y is already isolated, it seems clear that any x substituted in the equation yields a single y, so this y equals square root of x plus 5 is a function. And a little cheater's rule, if y has an even power, the equation is most likely not a function. And that's something you could get into later, and I'm not guaranteeing every time, but most likely it's not going to be a function. You still have to check it and prove it. Alright, so how do we evaluate functions? I made a point of saying that this is not multiplication, it's evaluation. So what we do is we use this idea of parentheses a lot, parentheses around the x here. When I substitute x equals 1, I'm going to take this x and replace it by a 1. And on the right-hand side of the equation, I'm going to remove this x, the 2x minus 3. I'm going to remove that x, and I'm going to use parentheses and put in the 1. So 2 times something minus 3, right? It varies. It's a variable. In this case, it's a 1. 2 times 1 minus 3 is 2 minus 3, which is negative 1. So we would say f of 1, the function evaluated at 1, is equal to negative 1. X equals 1, y equals negative 1. Same thing. If we replace x by negative 3, I put negative 3 inside parentheses to multiply it by 2 where the x used to be. 2 times negative 3 is negative 6. Negative 6 minus 3 is negative 9. And it's not just numbers that we can evaluate a function with. We could use variables or even expressions. Here, I want to replace x by x minus 1. So wherever there was an x, both on the left side of the equal sign and the right side, I replace it with x minus 1. And on the right side, I use parentheses saying 2 was multiplied by all of x. Now 2 is being multiplied by all of x minus 1. Distribute. 2 times x is 2x. 2 times negative 1 is negative 2. Don't forget your negative 3 hanging out the side. 2x minus 5 would be our result when we evaluate at x minus 1. 4 pi r squared. First, we replace the r with 2. I use parentheses when I take the r out, put the number in. Order of operations, 2 squared is 4. 4 times 4 is 16. This is the exact answer. If you're using the homework website webassign.net, WebAssign wants 16 pi. Pi is not 3.14. Pi is pi. So use the exact answer unless it tells you otherwise. When r equals 1/2, put in 1/2 for r, square it. 1/2 squared is 1/4. 1/4 times 4 makes 1 pi. And when r is replaced by 3r, we square 3r, so that's 3r times 3r times 3r, which is 9r. I did that too many times. That's 3r times 3r, my bad. 9r squared. 9 times 4 is 36. Pi r squared, our new formula. Alright, so a piecewise defined function, f of x equals x squared plus 2 for the x values that are less than or equal to 1. Whereas it's the piece 2x cubed plus 3 for the x values greater than 1. And this is a domain restriction right here, and a cut value of 1 where it cuts from the first piece to the second piece. To evaluate a piecewise defined function, let's suppose x value is negative 2. And so I ask myself, is negative 2 bigger than 1? No. Negative 2 is less than 1, so I'll use the top piece. F of negative 2 is negative 2 squared plus 2, which is 4 plus 2, or 6. For an x value of 1, 1 is not bigger than 1. 1 is equal to 1, so again I'll use the top piece. F of 1 is 1 squared plus 2, which is 3. And an x value of 2, 2 is greater than 1, so I'll use this bottom piece. So f of 2 will be 2 times 2 cubed plus 3. 2 cubed is 8. 8 times 2 is 16, plus 3 gives us 19. Evaluating a piecewise defined function. Alright, here's a take back to section 1.3. Find all the real values of x such that f of x equals 0. This is a fancy way of saying find the x-intercepts. Let y be 0, let f of x be 0 because y equals f of x, and solve. Replacing f of x with 0 in this equation, 0 equals 5x plus 1. Subtract the 1, divide by 5, and we have our real value of x, such that f of x equals 0. If f of x is 12 minus x squared all over 5, I'm going to replace f of x with 0. Now to solve 0 equals 12 minus x squared over 5, I choose to multiply both sides of the equation by 5, my denominator. That way it cancels out on the right hand side. And the nice thing about a 0 is I still have 0 times anything is 0 on the left. Add x squared to both sides. If x squared equals 12, then x is plus or minus the square root of 12. Y plus or minus, x squared tells us there's two options. One's positive, one's negative. Square root of 12, using the product property, is the square root of 4 times 3. We know the square root of 4 is 2. We have no idea what the square root of 3 is, but we keep that plus or minus out in front as we had it over here. In general, and I'll show you this a couple of times, but when solving a rational function equal to 0, it turns out that you solve the numerator equal to 0, because our first step is always to multiply both sides by the denominator. X cubed minus x squared minus 4x plus 4 now equals 0. If I have 4 terms, I'm going to try factoring by grouping, and I group these first two, x cubed and x squared, and I notice that they each have at least x squared in them. If I factor x squared out, I'm left with x, a minus, and don't forget the 1 as your placeholder. I always use the sign in the middle, so I bring that negative sign down. What do 4x and 4 have in common? They have a 4 in common. But remember that negative sign in the middle, I've actually factored out a negative 4. So I'm going to take negative 4x and divide by negative 4 to get x. I'm going to take positive 4 and divide it by negative 4 to get a negative 1. And if I look in my second row here, I have x minus 1 in common. I bring that out. I'm left with an x squared minus 4. And I could keep factoring using the difference of squares formula, or I just use the zero factor property that says if you multiply two things together to get 0, then either the first one is 0, x minus 1 equals 0, or the second item is 0, x squared minus 4 equals 0. Solve them individually, x equals 1, or x squared equals 4. Remember to always simplify this. X is the plus or minus square root of 4, which is plus or minus 2. List them out. Negative 2, 1, 2. It's nice to have an order from least to greatest, but not required. Let's take a look at translating words into math. Write the area A of a square as a function of its perimeter. So area as a function of perimeter. So I want perimeter to be input and area to be output. Now it's a square, so we're going to let S be the length of a side of the square. The area is S squared, and the perimeter is 4 times S. I want the variable for the area equation to be P. Well, P is related to S, S is related to A, so I'm going to solve the P equation for S. I'm going to divide both sides by 4. S equals P over 4. And then I'm going to substitute this into my area equation. Instead of area equals s squared, area equals p over 4 all squared, which is p squared over 16. Write the area A of a circle as a function of its circumference. So we find the formulas for circles. Area, pi r squared. Circumference, 2 pi r. I'm going to write area, keep the area formula. I want to use c as my input, so I'm going to solve c equals 2 pi r for radius. R equals c over 2 pi. I'm going to replace that in my area equation. Instead of pi r squared, I now have pi times c over 2 pi all squared. That's c squared over 4 pi squared. The pi in the front, the pi's squared in the denominator simplify to give me a c squared over 4 pi in my denominator. Last example. The height y in feet of a baseball thrown by a child is y equals -1/10 x squared plus 3x plus 6, where x is the horizontal distance in feet from where the ball was thrown. Now, this is not the same equation for every child, just for this particular example, this child. Will the ball fly over the head of another child 30 feet away trying to catch it? Assume the child who is trying to catch the ball holds a baseball glove at a height of 5 feet. Alright, so the height is y. I want to know if they're 30 feet away, right, horizontal distance in feet, 30 feet away, what's going to be the height of the ball? So let's put 30 in everywhere we see an x. Replace the x with the parentheses and 30 inside. I'll have a -1/10 30 squared plus 3 times 30 plus 6. 30 squared is 900. 3 times 30 is 90. Don't forget the plus 6 and the -1/10 out in front. -1/10 of 900 is -90. Plus 90 plus 6. The -90 and the positive 90 cancel each other out, give us 0, so it's 6 feet high. So what does this in blue tell us? It tells us after the ball travels 30 feet horizontally, it will be at a height of 6 feet. But the other kid is holding his glove at 5 feet, so it's going to go over his head, and he's not going to catch it. Bummer.